In this video lecture, I'm going to be giving you a short introduction to the derivative of a function. So let's suppose that we were interested in finding the slope of some function. So we'll call it f of x. We want to find the slope of f of x at some point. Right, so what I've drawn in the diagram here is I've drawn a function on the xy plane. So this function is denoted f of x, and here I've got a point on the function, and this point has x coordinate labeled x, and then of course image f of x. So if we had to obtain the image, we would read it off the y-axis right there. Right, so immediately looking at this question, find the slope of f of x. Yes, at some point x, then observe that because this is a curve and not a straight line, it is not possible using the previous tools that we have at our disposal. However, how do we calculate a slope from our previous knowledge? So recall that the slope of a straight line, so that is what we know. We can deal with straight lines, not arbitrary curves. So the slope of a straight line is given by the change in y over the change in x. And in order to compute this, we require two coordinates or points. So right now we only have one point of interest and not two, making it impossible to make use of this formula. However, what if I did select another point on the curve? So let's just say it was h units away from x, meaning that it is the point x plus h on the x-axis. Right? Then observe that its image will be given by f of x plus h. So that point there is described by x plus h, comma, f of x plus h. Right, so that is what we have. And now using these 2 points on the curve, I could then compute the gradient or the slope of the straight line passing through those 2 points. So let me draw the straight line that would pass through those 2 points. Right, so if I had to draw that, right, so here is a straight line, it's drawn in red, it passes through 2 points. So just going back to some of the previous definitions that you would have encountered, a straight line which intersects a curve at exactly 2 points is called a secant. So we have a secant which has now been drawn, and it intersects f of x at 2 points given by the points that I have stipulated on the curve. So the gradient of the secant line using that formula, of course, now is going to equal to the change in y over the change in x. So what is happening at y? So the y coordinate from the second pair is f of x plus h, and then I need to subtract the y coordinate from that pair, so I'm subtracting f of x, and then in the denominator I'm taking the x value from the second coordinate, which is x plus h, and I'm subtracting the x coordinate from the first pair, and that is x. So simplifying this, observe that the gradient of the secant is f of x plus h minus f of x divided by h. Now, keeping this in mind, this was the gradient of the straight line passing through those 2 points. However, we are interested with what is happening at point x, right? So not at x and x plus h. So I do not want the rate of change between those 2 points. I want to know what is happening precisely at x coordinate x and y coordinate f of x. So how would I proceed to obtain that type of conclusion? So essentially what we want to do then is we would like this point x plus h to get closer and closer to x until it coincides with x. So what we are essentially doing is, if I'm moving closer, that means I am making x plus h move towards x in that direction. So if, for example, I wanted x plus h to be at that point on the x-axis, then observe that the point I would then work with on f of x is now that. And then let's go closer to x. So observe if I wanted this to be x plus h. Then observe that the point I would work with on the curve would then be that. And that means that the secant line would now pass through these 2 points. What has happened when I ensured that x plus h was closer to x? Observe that the secant line dropped. It fell in that direction. So once again, if I move this point arbitrarily close to x, if I make it coincide with x, then what's going to happen? Then observe that that secant line would now drop and become a tangent line. So essentially what's happened here is, as x plus h goes closer to x, the secant line drops until it eventually becomes a tangent line at that coordinate x comma f of x. And what was the reasoning, or how could we summarize this mathematically to explain that the secant dropped to a tangent? Right, so observe what had happened. X plus h was taken closer to x, which means that h tended towards 0. So as h becomes sufficiently small, x plus h will eventually coincide with x. That is the idea that we are working with here. So when h tends towards 0, observe that the gradient of the secant now approaches the gradient of the tangent line at the coordinate x comma f of x. So we have that gradient of the secant approaches the gradient of the tangent line. So the gradient of the tangent line that we've just mentioned is now obtained by simply letting h tend towards 0, so taking the limit as h approaches 0 of the gradient of the secant, which was f of x plus h minus f of x divided by h. So essentially we have now obtained a description for the slope of f of x at some point x, and it is given by the gradient of the tangent line that passes through that point x comma f of x, because remember, for every x you have a y coordinate f of x. So that's an important thing to keep in mind. If you're finding the slope of a curve at some point, it amounts to finding the slope of the tangent line at that point on the curve. However, keeping this in mind, this formula is actually the derivative of f of x, which we now denote by f prime of x. So the derivative of f of x is the limit as h approaches 0 of this expression. And just observing from the motivation that I've written down, observe that the derivative of f of x actually represents the slope of the tangent line at the point x to the curve f of x. Right, so derivative of f of x. Right, so it's important to understand what happens geometrically, so to have both the algebraic and the geometric interpretation. So whenever you're finding the derivative of a function f of x, you are essentially finding the slope of the tangent line to the curve at that point f of x. So keeping that in mind, we can now answer the following question, which deals with actually finding the equation of the tangent line to some curve, because we know that f prime of x actually denotes or gives us the value of the slope of the tangent line to the curve. So let's use all of the tools that we have now learned. Right, so we have our function f of x, and we would like to find f of x plus h. So all you'd have to do is replace x by x plus h. So wherever there's an x, I'm going to write down x plus h. So that means x plus h squared plus 2. Simplifying this, I now obtain x squared plus 2xh plus h squared plus 2. Right, why did I want to compute and find out what is f of x plus h? Because remember, I want to find out f prime of x, which actually gives me the slope of the tangent line to our function f of x at some point x. Right? But in particular, we are going to be focusing at x equals to 1. But let's come to that later. Right, so from our previous slide, we have our formula for f prime of x. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So now plugging in all of the information, that is why I've computed f of x plus h, because I needed it. So I now am computing the limit as h approaches 0 of f of x plus h minus f of x. So I am taking this expression and I'm subtracting that one from it. So when I subtract x squared minus 2 from this expression, observe that the x squared falls away and the positive 2 will fall away. So all I'm left with in the numerator is 2xh plus h squared divided by whatever was in the denominator, which is h. And then simplifying the limit as h approaches 0, I can factor out h, so I'm left with 2x plus h divided by h. Observe that these cancel, and I'm now computing the limit as h approaches 0 of 2x plus h, which gives me a final answer of 2x. So observe that f prime of x equals 2x. So the slope of the tangent line to f of x at x is described by 2x. But I want the slope of the tangent line to f of x at x equals to 1. So I want f prime at x equals to 1. So substituting that in, observe that our slope is 2. So this is the slope of the tangent line. We are working with a tangent line, meaning we know it's a straight line. So keeping that in mind, the equation of the tangent line has form y equals mx plus c, because it's a straight line, and luckily we've already got the gradient at that point. So what we are required to obtain now is the y-intercept. Right, so since we are working with coordinate x equals to 1, so we're working with x equals to 1 and f at 1. So let's quickly find out what is f at 1. Here is f of x, plug in 1. What do you get? 1 squared plus 2, which is 3. So I'm working with the coordinate 1, 3, and I'm working with the gradient of 2. So I've got the point and I've got the slope, which means you could now quickly solve for the straight line using the point slope form. Point slope form tells you that y minus y1 equals to m into x minus x1. So substituting everything in, this is y minus 3 equals to the gradient, which is 2, multiplied to x minus 1. And then simplifying this, I've got y minus 3 equals to 2x minus 2, which implies that y equals to 2x plus 1. And that is precisely what we were required to find. We wanted to find the tangent line to that curve at the point x equals to 1, and which is why we had substituted in x equals to 1 into the derivative. So please ensure that you understand the motivation of the derivative and how you can apply it. Going forward, we will look at other formulae on how to compute the derivative without requiring limits, meaning we wouldn't have to use first principles to come to the final answer of 2x.